Start.
So good morning to all. So my name is Martensite. I am working in UGR as a lecturer in metallurgical department. So today we will discuss about the Martensite transformation. So Martensite, first we should know what is the Martensite. So if you see, if you have read iron carbon diagram, so there are lots of phases in the iron carbon diagram like alpha chloride, austenite, lead boride, and light, etc. So in that iron carbon phase, equilibrium phase diagram, so Martensite was not engaged. So Martensite, what it is a non-equilibrium phase. Okay. So austenite, light, lead boride, all these are the equilibrium phases. But Martensite is not equilibrium phase. So if we define this Martensite, so it is a supersaturated solid solution of carbon in the alpha ion. Okay, so this it has the BCT structure. Okay, so BCT structure is changes with the increasing the carbon percentage. So if you see, so 0.2% of carbon up to 0.2% of carbon. So the Martensite structure is remain the BCC after increasing from 0.2% of carbon. So Martensite is remain BCT because BCT is increased with the carbon percentage. Okay. So how it is increased? So what is happening in the Martensite transformation? So we are heating the sample to a austenite temperature. So after that we are suddenly cooling to the lower temperature, what we call the Martensite start and Martensite end. So within a few seconds, within a microsecond, so it comes to the Martensite starts. Okay, so this is also known as the diffusionless transformation. Okay, because there is no sufficient time for carbon atom to diffuse. Okay, so this is called a diffusionless transformation. So next, in this graph you can see, so this is the x-axis, this is the lattice parameter, this is carbon content, and it is C, and below it is A, and middle this is C by A ratio. So tetragonality, what we have discussed is tetragonality. Tetragonality we can indicate by this C by A ratio. C means in Z axis what is the distance of unit cell. A means what is the distance of X axis, and B means what is the distance in Y axis. So in tetragonality, what is the relation among the A, B, C? So A is equal to B but not equal to C. Because what? So carbon atom is trapped in the octahedral side. So octahedral, due to carbon atom trapped in the octahedral side, what is happening in the unit cell is it expand in the C axis. So the C by A ratio is greater than 1 in the BCT structure. Okay. So we can see this is a mechanism of transformation when the material is heating to a austenite temperature and rapidly we cool to the lower degree temperature, what is called Martensite starts temperature and Martensite ends temperature. So this is a there is a during the cooling from austenite to Martensite, there is very less movements of the atoms. So it is a displaceable transformation that takes place by cooperative movement of a large number of atoms. Okay, this is also known as military transformation. Military transformation means so relative displacement of atoms is fraction of interatomic distance. Okay. So you can see this is a BCT orange wall is denoted as iron, and this is carbon, and small one is carbon bracket side. Okay. So in which BCT structure, what is happening is that so this carbon is present over the octahedral side. So due to this trap on the octahedral side, this axis, this is the x-axis, sorry, this is the c-axis. Okay. Suppose I take this is a or this is a y. So y means b. Okay. So if I see, if we go to the let's go to the whiteboard, and let's put this input yes. Okay. Let's see. This is C, okay, this is Z axis, right? Z axis, this is X axis, this is Y axis. So this part is B, okay, sorry, this is B, and this is A, and this is C. So trilaterality in Martensite, so A is equal to B, A is equal to B, but not equal to C. Okay. So when A is equal to B, that equal to C, then Martensite structure will be your BCC, body central cubic crystal. And when B A is equal to B, not equal to C, then it is known as BCT, BCT, body central crystal. Okay. So this I want to. Let's go to the presentation. Okay, so when CYA is 1, that is BCC structure. Okay, and CYA is so let's go to the next. So this is the TTT work actually. So TTT, and let's go to next. What are the major characteristics, important characteristics of the Martensite transformation? So first is it is an extremely rapid transformation. So due to which the diffusion of carbon is restricted and carbon atoms are trapped in the octahedral side, due to which the distortion occurs, and that distortion change the crystal structure from FCC to BCT. Okay, so it is a transformation is rapid, extremely rapid. Second is it is athermal in nature. Athermal means when transformation is over, so it is, you can go to this slide. So when the slow cooling is occur, we are getting the polarity. Okay, what's the polarity? So when we are just increase the cooling rate, then we can get maybe magnetic or maybe the fine polarity. So, but when we bypass this C curve and we come to this temperature, then we get the Martensite. Okay, this is Martensite start, this is Martensite end. So let's go to next. So this is athermal, means it is this transformation rate is not dependent on time or not dependent on temperature, because this is a very rapid process. Next, as it is diffusion process, so this in this transformation, then composition is remain changed. If you see what quadratic transformation, what we have discussed. Suppose this. Just suppose Suppose these are the given. Okay. So collinetic transformation, there are lamellar structure. We know that there is a lamellar structure, and what is the composition of collinetic? One is alpha ferrite, another is cementite. Okay. So and ratio of the alpha collinetic is 8:1. 8:1. 8 is your what? Collinetic is alpha ferrite, and 1 is your cementite. Okay. So here it is this type of structure is we are getting in the collinetic transformation. Okay. So this is a lamellar structure. Yeah. So this is in this Martensite transformation. So as it is what? It is a diffusion process. It is diffusionless process. So there is no long atomic movement. There is no long atomic movement. Then fourth one is surface relief. Surface relief means when the Martensite transformation is over, the Martensite crystal, some Martensite crystal is displaced above the austenite, okay, and some Martensite is displaced below the austenite. And the flame where this transformation is occurred is known as your habit plane. Okay, so this habit plane in the austenite is neither distorted nor changes. Okay, but in this preferred plane, this transformation, what Martensite transformation is. So the next one is your temperature. So how this MS temperature is depend on alloying element. If you see, we have already discussed when we have studied the ETT form. I have discussed the MS temperature. MS temperature, when we are adding, then MS temperature is decreases. Okay, MS temperature is decreases. Amongst the alloying elements, the most affecting element is carbon. Okay, so actually this is Android's. This is called Android's equation. MS temperature equal to 539 minus 423 into percentage of carbon minus 30.4% of manganese, like this you can see. So major contributing for lowering the MS temperature is your carbon. Suppose we are taking steel. So steel is suppose steel is composed of iron and only carbon. So I take only 1% of iron. Okay. So what is your MS temperature? So 539 minus 423 into 1 means 539 minus 423 means how much? 9 minus 3 is equal to 6. 1. So 160. So if I take the composition of steel where carbon is containing 1% and this remain and other alloying element is subset. So MS temperature we are getting 539 minus 423, that is equal to 160. Okay. So in this way you can see the MS temperature is how it is there. So if you see morphology of the Martensite, there are two types of Martensite. One is lead Martensite, another is lead Martensite. Okay. So lead, what is lead? If you see, lead is, let's go to the whiteboard. When the bunch of branch is kept on something, when the bunch of branches is kept in one place, so how it is looking, that we call them lead. Okay. Suppose this is a grain. So in Martensite, this type of structure is okay. this type of. Okay, or plate martensite. This is also called lenticular martensite. Lenticular shape martensite. Okay, lenticular means lens shape. So if you see this type of martensite is in flat martensite. Okay, so this is a flat martensite. This is a flat martensite. That means when the bunch of branches is kept in a single position, how it is looking, we are called that is length. So this shows like that. So this is the length martensite, and this is a flat martensite means looking like lens. Okay. Another is MS temperature. So left martensite is get in when MS temperature is high. So MS temperature, when we will get the MS temperature high? So when the carbon percentage is low, or some carbon low means 0.02% carbon, or medium means maximum 0.2%, 0.3%. Okay. So MS temperature is high on low carbon steel and medium carbon steel. So left martensite we are getting in the low carbon steel and length carbon steel. But flat martensite. So when we are getting the flat martensite, when the MS temperature is low. So when the MS temperature will be low, when the carbon will be high. We have already discussed in this equation. So here it is already there. Suppose carbon is high enough. Okay, high enough. Suppose 3%. So suppose 2%. So 2%, 1.5% maybe. Okay, you can see. So this will be very low. So MS temperature will be low. So at that time you will get the flat martensite. So this was the actually martensite. Okay. So let's close the lecture. Thank you.